Okay. You guys have your next assignment on Moodle. Have you checked it? Has everyone checked the assignment?
Yes, I have two questions.
Yes, sir.
First of them is it's about second point.
Let me bring the assignment. Give me 1 second, please. Assignment 2. Yes, please carry on.
Point B, using the following functions, find the optimum solution. As I understand, we should use all three methods, bisection, Newton, and regular falsy for each function. Or how we should done with this point?
Yes, you have to first, what you have to do is you have to implement the three. First of all, exercise 1, I've written implement each of the 4. It's not 4, it's 3. Actually, I had written 4, but then I thought it would be too much, so I reduced 1, then I forgot to change 4 to 3. So please make the correction, implement each of the 3 univariate optimization techniques. Okay, so bisection, Newton's method, and regular falsy. So these 3 you have to implement in whatever language you know. You have to provide your code, and you have to actually prepare a report in which you have your code and you explain how you have written it. So I know that the code is genuine and you've done it by yourself and not taken it from any website. Then the part B asks you, okay, now you have to test or find the results of, find the, the optimal solution for these two functions. So for example, if I apply bisection method on the first function, it should give me my optimal solution. And the same for Newton and regular falsy. So using these 3 methods, apply it on these 2 functions and show me the results.
Okay, thank you. And the second question and last question. Will be the cleanness of the code be evaluated? I mean that should we divide each function and make a function, or we can just implement the code into one main?
My dear, this you can code as you wish. The more proper and proficiently you code would be better, okay? But this is not a coding class, a lecture, okay? So I cannot say, okay, why did you write such a bad code? Or why did you make it look so confusing? I cannot degrade you for doing that, okay? Because that's not the intention of this assignment. But for me to understand better, I need you to write your code as easy and as understandable and presentable as possible. And it should be, not difficult to follow. But again, it's up to you as you wish. You want to write it in functions, you want to put the whole thing in main, it's up to you. I don't care.
Okay, thank you.
You're welcome. Any other questions regarding the assignment?
Hello, yes, I have a question.
Yes, sir.
Is it fine that Newton's method converges but fails to find the correct root?
It converges but fails to find the correct root. How is that possible?
Well, I don't know. It takes.
But the other methods are doing fine?
Other methods are doing fine. And what's interesting, Newton's method fails to find the correct root only in one of the functions. You gave us 2 functions, and in one of them it finds correctly, and in the other it fails.
Well, put it in your report, then I will see. I will check with my solutions because I have to check and see whether it's true or false. Do your best, make sure your code is correct. And we talked about Newton's method and the cases in which normally it doesn't converge or it fails to work actually. So if any of these equations fall in that category, then probably you can explain it. If not, then I recommend you to double check your code, test it for other functions and make sure it's working correctly. And then if not, then you can just put it in your report. I'll take a look.
Okay, thank you.
Thank you. Any other questions, guys? So I'm assuming that everyone is able to follow and everything is going on well. I was looking at your grades. Ainur has actually uploaded your grades for your assignment 1 and quiz 1. Thank you, Ainur. And the quiz, well, the average is 70. Okay. But the assignment one average is 92. So that means assignment everyone is able to do, but the quiz, very few actually got it right. I guess only maybe 3 people got the full score. Yeah. Okay, good.
Hello,
So,
Professor.
yes.
Hello, how are you?
Oh, hi, I know. Yes.
I want to add something
Uh-huh.
regarding the quizzes.
Uh-huh.
Actually, I have noticed some copyright things. So it's kind of reminder to all the guys that unfortunately or fortunately, I know you all well and I know who you are friends with, and it's really obvious
Okay.
that so maybe from starting from the next time, I will give 0 for the quizzes if I will notice some copyright things.
Okay, that's well, you heard what she said, guys. This is exactly what I told in the beginning. I know you guys have these private chats, and if I just get one hint about those things, and if I get just one proof, believe me, I will report this to the office, and probably you can be even I don't know, maybe you won't be allowed to graduate. Okay, so don't let me do that, because I've given you the warning in the very beginning that I do not want dishonesty. Okay, this is already easy enough. I made the course much more easy enough. You can ask Ainur, you can ask your other students who have graduated and taken this course before with me. This time it's far much easier. Okay, I'm not trying to give you guys a hard time, but if you want to play games with me, trust me, I'd be the worst person in the world you've ever met. Okay, so don't let this happen, please. Okay, if you have any if I see any involvement in any private chats, any answers being given out over there, trust me, the person who's providing the answer and everyone in that chat would be reported to the school. And as Ainur said, next time we'll be following the trend in your quizzes and your assignments. We know when it goes up and when it goes down, and based on that, how you're performing. If we see any funny trends, trust me, I do not have any reason not to report you to the school office. Okay, so this is a last warning. Thank you, Ainur, and she has been actually kind enough to actually grade you. If I were her, I would just give you guys a 0. So she's giving a last warning, and from next quiz onwards, now that said, next week you'll have your second quiz, and I'm going to see how it's going to go over there. So next week you'll be having your second quiz. And a second quiz will be covering everything from the very beginning till what we study on Thursday. Okay, and based on that, I and Ainur will decide on what actions should be taken. Okay, any questions regarding the assignment? Okay, well, let's finish what we had to do, because we are kind of a bit lagging. Again, we had this problem. Okay, so we talked about interval halving last time, and then we had to talk about Fibonacci search, and I had asked you guys to study about it. So today I'm going to randomly select some people and see whether they have studied about this. Okay, let's begin with Sultan. Sultan, can you explain Fibonacci search to me, sir? And
Yes,
no is not an
course.
answer. It's not an option. You have to explain.
Yes, I said I will.
Oh, yes.
Sorry.
Okay, please.
So what we do, we basically take 2 points at which we have, at which we satisfy, at which the function satisfies the unimodality assumption. So we have such shape, and from endpoints, from these 2 endpoints, we select 2 points, which are located at distance L star, which is given by ratio of 2 Fibonacci numbers, Fn minus 2 divided by Fn times L naught.
Why do you start with 2? K is equal to 2?
Sorry?
Why do you start with Fn minus 2? Why did you put K is equal to 2 over here? Why not L1? Why L2?
Why L2?
Yeah.
Well, maybe it's the second experiment.
It's because
Well,
when
actually,
first time when you start doing it, you always have to take 2 experiments. From the next iteration onwards, you always take 1 experiment. That's why you always increment by 1 after this. But for the first time, you start with L2 because you're taking 2 points. Okay.
okay, so we start from L2. L2 is given by this. Well, actually, I saw the explanation in that PDF file, and
It's, I think it's the same. I've just tried to make it more fancy and good looking over here. Yes. So basically, if in the PDF file, I'm not mentioned of what should be the minimum value of n, but over here, if you take n to start from 2 or anything that is 2 and greater, okay. What we can do is we can write it as fn minus k. We don't have to write the +1 because +1 is in both cases, so you can remove it. Okay. So this is basically the same equation. Please carry on.
And then we select 2 points, which are located at this distance, L naught, L star, and we discard either this part or this part based on the so that the remaining part will satisfy the unimodality assumption. So in this case, we'll probably so in the end we'll have either this new distance or this.
Okay.
In this case, I think we will stop with this, right? And then we repeat again. We find new L naught, which is given by, again, ratio of 2 Fibonacci numbers times new distance. And I have one suggestion here to simplify everything. I think we can write it in this way. 0, well, ratio of 2 Fibonacci numbers is constant if n is large enough. 0.
If n is large enough. I know what you're saying, but that's if n is large enough, right?
Right, yes.
Okay.
Generally, I think these numbers have no meaning by themselves. We're just interested in their ratios, so why not to take the constant? Maybe we can even
yes,
round
but
to
I mean,
0.4.
you have to, well, you get the constant only if you know the relation between the 2 Fibonacci numbers and when you generalize it. So if you didn't know this generalized form, there was no way that you would come up with this constant value, right? So if you want to make life easy, yes, you can say, okay, we put 0.382, but when you become a professor and you have to explain why you have taken this constant, you have to explain that there is a relation between 2 Fibonacci numbers, okay, and this ratio is some constant value. So we'll be talking about it later on, but for now on, for the general case, we have this equation as shown over here, okay? Okay.
And then we repeat again and again until our L becomes small.
Okay.
Maybe we even set our N from the very beginning. I think.
You have to set N from the very beginning. Let me, thank you, Sultan. Now let me quickly just go through it for those of our friends who have not understood clearly. So basically, I told you what a Fibonacci number is. You know the first 2 numbers, F0, F1 is equal to 1. And after that, for any n value, it's the sum of the previous 2 consecutive Fibonacci numbers, okay? And we assume that in the beginning, we are given an interval from xs to xf, and the length of this interval is L naught. Okay, so given this, and in the beginning, we have to know what n is. And I'll tell you, well, this is a drawback of Fibonacci, but I will tell you how it is good and how it is bad. So given n and given this initial interval, what we do is, so basically we have L naught. This is given to us. So first thing, we set k is equal to 2, because in the first iteration, we have to find 2 points, x1 and x2. Okay, so since we are doing 2 experiments, we put k is equal to 2. And then we compute something called the L star k. Now, what is L star k? L star k is this ratio. That means if I put k is equal to 2, it will be f of n minus 2 divided by f of n times L naught. So it is some portion of L naught, okay? So what we do is we add this L star k from the starting. So xs plus L star k would give us x2, okay? And xf minus L star k would give us x1. So starting from the endpoints, we add and minus this L star, and it will give us 2 points on this within this interval. Okay. Now, given this, so basically we do this. Oh, sorry. So basically we do this x1 and x2, and we find these points. And then we use the unimodality assumption that we say that the midpoint, so should be, so we compare the functional value at this point and this point, and based on that we can say, and of course we know this point, so we say whether we have which part we have to discard. Okay, we either discard LK, and one thing that you have to keep in mind is this LK, this is LK, and this distance is also LK. Can be either case. So LK is actually L over here, L2 is equal to L0 minus L2 star. So L2 star can be any distance taken from either side. So whatever you reduce from or deduct from L0 will give you LK. So LK can also be this distance or this distance. Depending on which part you want to eliminate, you will either keep this distance up till here, this LK, or so that means you will eliminate this part, or you will keep this distance and you will eliminate this part. So your new interval would be either one of these two. Okay, so that's how you find your LK. And based on that, you compare. Now you see that whether this K value which you're incrementing, so K was equal to 2 initially, then we check if K is equal to N or not. If it's not, then you increment K and you go back to step number 2 and you keep doing this until K becomes equal to N. So in Fibonacci's search method, what you do is you know the number of experiments you want to conduct, that is equal to N. And you do reduce the size or reduce the length of your interval based on the number of experiments that you have predefined. Okay, so if I say that N should be equal to 5, that means I only evaluate these points 5 times, and when it finishes, I stop. Whether I have reached the optimal solution or not is not a guarantee. So this basically just gives you an interval. It will return only a small or reduced interval of uncertainty. Okay, it doesn't return the actual solution. All right, because we are iterating, or we are comparing the condition based on N. Okay, not based on any epsilon value. So so for example, I tried to explain the same thing. So if we have this interval, this is L0, I find 2 points x1 and x2. Assume that f of x1 is less than f of x2. So this guy is less than this guy. So we know that everything over here is unnecessary and we can just remove it. So our new reduced interval would be this guy. So xf to, xs to x prime f. So we name x2 as x dash f, okay? So now over here, what we have is now, why do we increment k by only 1 and not 2 or any other value over here? That's because after the first iteration, and when we have a reduced interval, one of the experiments from the previous iteration will always be within the interval. So this x1 actually becomes our x dash 2, and now we have to find another new point, okay? And that new point would be x1, x dash 1, okay? So again, this point is what we call L star 3. It is equal to the length of L2 minus L2 star, okay? It's this distance. So as you know that this distance is the same as what? This distance, the distance between the 2 points that we found in the earlier iteration. And this guy is equal to, obviously, same as L2 star. So the L2 star or L2 star. So the distance of x1 or x2 from the endpoints. And this will be our new L3, and this will be our L star 3, okay? And so basically, using these equations that I've given you over here, this equation and this equation, you can calculate L2 star and L2, and you can write L2 actually in terms of L0 itself, okay, or L3 in terms of L0. So if you do J number of experiments, so suppose we have a total of N experiments that we want to conduct, and out of N, we are on the Jth experiment. So after finishing J experiments, the remaining length would be, so L star J can be written in this general form, which Sultan said we can reduce this into some constant value. Yes, but in order to find, to give you a general form of how we got that constant value, it's good to know how this works. So basically, it is the ratio of Fibonacci number divided by a Fibonacci number, which is not the consecutive, but the one before the consecutive preceding Fibonacci. So if this is n minus 3, it is not n minus 2, but n minus 1. Okay, so that would be L star j, and Lj would be the distance, which we saw over here, and it is equal to the previous length of the interval minus L star j. That means L star j that you get over here, which can be written in terms of this Fibonacci ratio. Okay, so assume that now when j becomes n. Okay, so basically after j experiments, the ratio of Lj to L naught would be this. And if j is equal to n, we would get this. So this f of 1 we know is equal to 1. This would be 1 divided by f of n. Okay, so we can in the very beginning, we can actually specify the length of our interval by identifying what the value of n should be. Okay, so by knowing the value of n that we want to find, we can find 1 divided by f of whatever n we want, and that would actually give, and we know L naught, so therefore we can find the final length of our interval in the very beginning, beforehand. Okay, one more thing I wanted to tell, I forgot, probably I'll remember. So any questions so far? Good. Okay, with that said, let me, where is that guy? Where is your lecture? Okay, so let's go back to you guys can see my screen, right?
Yes.
Okay, so this is basically what I've done. The derivation or more details is given over here in my lecture slides. You can take a look over here, and I've shown you this. So we get here. Where's my pen? Let me get my pen. Okay, so this is what I showed you in the slides. Okay, so the ratio of the final interval to the initial interval would be 1 divided by f of n. Okay, now so basically, and also like there are some examples, so please take a look at, well, I guess you have done it. So there are some examples at the end of this lecture, which will give you some idea of how to use this or how these methods work, or where do we use this, what is this ratio thing, okay? Now, what are the limitations? What are the drawbacks of Fibonacci method? Well, obviously, in the beginning, we should have some given interval. That's okay. Another thing is we should know the value of n in advance, okay? And knowing the value of n in advance means you have, this is what I wanted to say. In Fibonacci method, if you have n is equal to say 27, you have to calculate f1, f2, f3, f4, f5 up till 27. So you need to do this calculation in order to obtain. So for example, if I want to use this ratio, 1 divided by f27, I should know what f27 is. To find f27, I should know what f26 and 25 is, and so forth. So basically, you have to find the Fibonacci values up till all 27 value for the 27th element. Okay, so that's what the number of function evaluations must be specified beforehand. Okay, now let's look at the golden ratio. Now, how does golden ratio improve over Fibonacci method? Does anyone know?
Because we don't need n, maybe.
We do not need n, yes, but can you give me another? I mean, in terms of this, where is my slide? In terms of this graph, can you tell me what is something that we do not know in terms of ln? Pay attention that every time in each iteration, we are removing some part, right?
Yes.
So in every iteration, we are removing some LK star. Am I right? Does everyone follow?
Yes.
So in every iteration, we are removing some part of the interval, and that part of the interval that is being removed is the L star K, right?
Mhm.
So over here, we are removing this guy. Then over here, probably if again, f of x bar 1 is less than f of x bar 2, then again, we will remove x star 3 and so forth. Now, the amount of interval that is being discarded or removed in every iteration is unknown. It's not a constant, okay? So this L2 star that we are removing over here is not the same as L3 star, okay? And depending on the value of n, so this value actually changes every time. So we cannot say, okay, the change in the amount of interval that is being discarded in every iteration is known or is constant or is fixed is untrue for Fibonacci. Okay. But when you go to this guy, the global section, in global section, we say that, okay, what I want to do is I want to say that in every iteration, whatever part I remove will always be a fixed amount. It will not be changing based on the value of k or n. Do you understand? So basically, let me see how I can put this. Is it understood, or do you want me to explain it again?
Can you please explain it again?
Okay, I'm looking for I have found a nice graph so that I can draw for you guys. And now I'm trying to look for it. 1 second, let me see if I can find it. Okay. Okay, now when you want something, it won't be there. Okay. Okay, so the golden, so basically what I want to say, okay, let me bring this guy. Basically, the golden method is the same as Fibonacci method. So many of you, when you work it out on paper on a line, and for some given example, you'll see that the way it is discarding the length, the interval is the same. The behavior is the same, except that in Fibonacci method, as I said, the ratio of the interval that is being discarded in every iteration is not constant, okay? And also obviously that the number of experiments should be specified beforehand, while in golden section, this is not required, okay? So, actually, I think I have it in my own notes here somewhere. I was looking for this guy. Okay, so basically what I'm trying to say is, let me draw it in a different way. Maybe that would be easier. So suppose I have, so golden ratio, oh, this is a terrible line. How do we draw straight? Okay, this is a straight line. Okay, let's say that this is a straight line. Okay, and we have 2 points, A, B, not B, let's I mean D. Okay. And let's say that there is a point, let's divide this like this. Let's call this guy B. Let's call this guy C, right? Now, if there is a distance from A and C, let's say that this distance is some distance tau. Okay? And this distance is some distance 1 minus tau. So the sum of, so the distance, the length of AD is basically 1, okay? So I divide AD into 2 parts. One is tau and one is 1 minus tau, all right? Is it clear? Now,
Yes.
so I have 2 points, then I have, so there's a point C at which I can make this division, okay? Such that tau plus 1 minus tau is equal to 1 and tau is greater than 1 minus tau, all right? Now, similarly, I can divide the smaller portion, and that means AC, which is of length tau, with the same proportion. That means I find some point B such that the distance AB is 1 minus tau. So this distance would be tau minus 1 plus tau, right? Am I right?
Yes.
Yes.
Okay. So now what I did is the actual line. So assume I've given you a line of length unity, and I say divide it into a proportion, two parts. So I take tau and 1 minus tau. Then the shorter part, I'm sorry, the longer part, that means AC of this unity line, unit line, I divide this also with the same proportion. So I choose another 1 minus tau, and I divide this tau into 1 minus tau and 2 tau minus 1. Okay? Is it clear?
Yes.
Okay, so now if I do this, what do I get? So this is basically the idea. Where's my mouse? The idea behind finding the golden ratio guy. Okay, so basically if I just take it for one length AB, okay, and I say that tau and 1 minus tau. So what I do is I take the length of the line segment, okay, which is 1, and over the length of the largest segment. The largest segment was tau, okay, and is equal to the length of the largest segment divided by length of the smaller segment, which is tau divided by 1 minus tau. Okay, so I'm taking this by this over this by this. And when you solve for this, for tau, you would get this number. Okay, and this number is what is known as the golden ratio. Okay, so a golden ratio, do you know the history or where it comes from? Why is it such an important number, or magical? They call it a magic number as well, but why do you think it's so? Anyone done a research on this?
Golden ratio is essential ratio in the nature. We can observe it with human body as a ratio of some bones. We can observe it flowers as a ratio of some leaves.
The placements of the petals, yes.
Yes. So the assumption.
Where did it come from?
Sorry.
Who was the first person who actually put this into our heads and this idea into our head? Who came up with this number?
Leonardo da Vinci.
Well, yeah, he used it in his drawings. Very good. I'm happy that you studied. Yes, and actually before that, the Greeks.
Archimedes?
Well, I don't know who, but the Greeks, that's what is written in the history. But when they wanted to make their buildings, there's a famous Greek monument. When they wanted to build it, they actually came up, they thought that this would be a number and it would have what they call a pleasing properties. So they wanted to take the length and the breadth of the building to have such a, basically this is what they wanted to do. So what they did is, where is my mouse again? So basically how do I put, this is your building. If I say this is my, what happened? Oh. This is my, say, D, and this is B. Okay, so the length and height. Then they said that we should take the values of B and B in such a way that obviously D plus B divided by D should be equal to D divided by B. Let me check if I'm right. Yes, yes. And they call this to be equal to phi. So obviously when you solve this, so basically when you solve this, you would get, so this would be the same as 1 plus 1 divided by phi is equal to phi. And so when you solve for this, you would get the what is that? The golden ratio, okay? So basically, this is the golden ratio. And so 0.6180, which is the value of tau. And taking this value, what we say, so how do we use it in our work? Forget about the Greeks. It says that if you reduce tau, okay, so where's my figure? Oh, I cleared away that figure. So in that figure, if I reduce tau from each side, okay, in such a way, I'm sorry, if I reduce the interval from the endpoints with the value of tau, I would be reducing the size of the interval every time in a fixed amount. Okay, it will not be something unknown like the Fibonacci. So basically, when you take the limit of n goes to infinity, as our friend said, the ratio of the Fibonacci, two consecutive Fibonacci numbers would be actually equal to tau. This is again a very interesting property. Okay, if you can try this. So if you want to compare these two guys together, the Fibonacci search and the golden search, we see that Fibonacci search uses Fibonacci sequence. So I have to calculate all the Fibonacci sequence up till the Fn Fibonacci, because n should be known in advance. The golden ratio, you don't have to do that. You have to use is tau. Okay. So except for the first iteration, every other step requires only one experiment to be evaluated in Fibonacci. And in golden, it's the same. Every step requires only one experiment. Okay. What is this requires to store the Fibonacci? Yes, you don't have to store it here. You have to know n beforehand. So the length of your final interval would be basically b minus a times t. I'm sorry, tau to the power n minus 1. So if you want to know the size of your final length, if after n number of experiments, this would be the reduced length of your interval. Okay, where tau is some constant value. Okay, but over here again, b minus a divided by f by n, depending on value of n, this would be something that changes every time. All right. So also I told you that this is the limiting case of so when you take the limit n tends to infinity, this will actually tend or converge to the tau value. Okay, well, that's all I wanted to talk about in this lecture. These are some examples, and I'm sure you guys have worked through it. I've actually given you the solution, so I see no point in trying to explain it. So these are some examples that you probably can work out. So this is an example where you use this ratio of ln divided by L naught and to find the value of n. And then based on that, you can, well, this is also for the exhaustive search when you compare with exhaustive search. What is this? 10% of the exact value. Well, okay, good. So work this out. Okay, I've solved everything for you over here. And let me look at this. Okay, this also, I have told you how to find this. Well, these examples, this is another example where you use the Fibonacci ratio, and you can find f of n should be this value. So you have to work out all the Fibonacci's values until you get to close to this. So for example, over here, when n is equal to 13 is 377, which is less than 468. Then you have to do one more, which is 610. So n would be 14. And this is again comparison of Fibonacci and golden ratio. And that's it. So work out these examples. These are good examples I put out over there. I'll be giving you some more tutorial questions and you guys should work them out, and you can expect them for your quiz next week. Okay, now let's move on to lecture 4. I want to finish this as soon as possible so that from next week we can get into some real problem solving or some applications of linear programming and simplex methods, which are much more used. Okay, so basically we talked about what is that called? The forgot the name. Positive definite and positive semi-definite. So what was the definition of positive definite? I'm going to ask someone. Let's see. Yerasil, could you please explain to me what is positive definite?
Yes, sir, I'm here.
Yes, please define positive definite. When is a matrix, or when do I say a matrix is positive definite or not?
Well,
it was in your quiz also, I believe, or homework. It was somewhere.
I think it was in tutorial or something like that.
Okay, tell me what is that?
Yeah.
What is positive definite?
Matrix is said to be like positive definite when
anyone want to help him?
When eigenvalues are all positive.
When all the eigenvalues are positive. Okay.
And non-zero.
If the determinant is positive.
Okay, what's going on now? Well, forget
Non-negative.
determinant. I did not talk about determinant yet. This is another technique I haven't taught you yet. For your quiz, you had a question on give an example of a function where whose Hessian is, I don't know, positive definite or semi-definite something.
For Hessian, it should be eigenvalues or positive, no?
Okay, if you want to have a positive definite matrix, the eigenvalues should all be positive, okay, not zero or negative. If you want to have a negative definite, the eigenvalues should all be negative. If your function is, oh, I'm sorry, your matrix is said to be an indefinite matrix if not all the eigenvalues are positive. That means you can have negative or you can have zero eigenvalues. That's when we say A is indefinite. Okay, and when A is indefinite, we cannot say whether this is a point of inflection or it's a saddle point or it's a point of it's an optimal point. Okay, so so please study this and pay attention to the definition. Now, the Sylvester's test is a test which we use for positive definite matrices. So if you want to know matrix, for example, if your Hessian matrix given to you is positive definite or not, you do not have to calculate the eigenvalues. All you have to do is calculate the determinant. Okay, so for a very simple example, so matrix A is said to be positive definite if the determinant of all its principal minors, I'll tell you what principal minors are, is positive. Okay, so let's see. For example, I've given you this matrix, and your matrix will be a square matrix. So the first principal minor would be, let me use my pen, would be the matrix of the size A11. So this guy. Okay, so every time what we do is we only take the first element, then so now over here, the matrix that we get, it would be of dimension 1, 1. Okay, so the principal minors are submatrices of the actual matrix that you want to evaluate. So the first principal minor would be A11, which is this element. So you take the determinant of this. So this is basically 1, which is greater than 0, and that is what I want. So all the determinants should be greater than 0. Now we go to the second principal minor. Second principal minor is now you take the submatrix of order 2 by 2, and you always start from the top left corner. Okay, so my next submatrix would be this guy. All right, now I take this guy, find the determinant. You know the determinant, this time this minus this time this. So 5 minus 4 is 1, greater than 0, check, correct. And the remaining, only the last, what is that, principal minor that remains is the whole matrix itself. So we have to take a matrix of size 3 by 3, and you calculate the determinant. You would see that it is, you know how to find the determinant, right? Cramer's rule, there are many other ways to do that. You have minus 56, which is less than 0. This does not satisfy this condition. Therefore, this guy is not positive definite. So isn't that easier? No?
Yes, it is.
It requires less calculation.
Yes, because you know the Cramer's rule, you know how to find determinant. It's just far more easier. Okay. Now, what I want you guys to do is I want you guys to study Sylvester's test to see what are the conditions for negative definite and for indefinite matrices. So this is something you will have to do, and it's a homework. Homework means you have to learn it, and if it comes in your quiz, don't tell me I did not tell you. Okay. So what are the other? I mean, how does Sylvester test extend for negative definite matrices and indefinite matrices? Find out the conditions and work it out, okay? Moving on, Taylor's, Moving on, we go to Taylor's theorem. Do we have any questions so far? No?
Or is it applicable only for square matrices?
But because we are working with Hessians, and since we are in Hessians, it will always be a square matrix, yes. For now, I do not know whether it's applicable for, I think it should be applicable only for square matrices, yes. But double check, I'm not sure. Because in our context, we are only working with Hessians and matrices that are square matrices, so I know it works for square matrices. Okay,
thanks.
so since you guys okay, I'll not give you this. I'll give you this in your homework probably. Okay, I'm trying to look. Okay, theorem. Do you know what Taylor series is? Did you guys have a course on numerical methods?
No.
You did not have a course on numerical methods in your second year?
No.
Okay. So do you guys know what Taylor series is?
Yes,
You should be knowing what Taylor series is. Come on.
We've heard something about it.
We studied it, yes.
Okay. So what is a Taylor series? A Taylor series is that when you want to approximate a function at a given point, you use this series, okay? So for example, to make it much easier, I've written it over here, but this is, I've taken it from your text, from your reference book. So, but to explain it much more easier, I will try to write Taylor series in a much more easy form. So Taylor series basically is f of x star. Oh, this is going to take forever. H plus h. Okay. So if I want to evaluate a function at some point x star plus h, where h is a small value. So we have this point x star. We know the function value at x star. We want to find the function value at some very close neighborhood of x star called x star plus h. Okay, so we can do that by doing this. So we have f of x star. Okay, plus then we have h. So you take the first derivative of f at x star. Okay. Then you take the second derivative, you have h squared now. And x squared divided by 2 factorial you get. You take the second derivative at x star plus, and you keep doing this until the, let's say, the nth derivative. So this is the first derivative, which is the second term, third term, until the nth term. Okay. So this, let's say, so the third term is 2. So the nth term would be n minus 1 divided by n minus 1 factorial. Okay. And this would be the n minus 1 derivative of f of x star. So basically, this is the Taylor series, or Taylor's expansion of this function. Is it clear? Yes?
Yes.
Okay, good. So now let's get back. So this is Taylor series. So basically, that's the same thing that I've written over here, but instead of like, so basically over here, we are trying to find, we know x star, so we are trying to find the point at x. Okay, so basically, finding the point at some x is equal to finding the point at x star, and you keep. So therefore, this basically can be written as what is this? This guy. Okay. So this is h. Okay, so if I put this as h, so I would have x. This is h. So if you replace this with h, okay, this guy is h, this guy is h, you would get the same thing that I wrote for you, okay? And this is up till the end. So for example, if you take a look at this example over here, so if the Fibonacci, so I've given you a function, this is a vector, okay, this x. So everywhere in my notes, if you see, I forgot this, if you see an x bar, it means that this x is a vector. It's not a scalar variable. It's not a univariate variable. It's a multivariate. So x actually has two components, x1 and x2. And this is the function defined for this vector x in terms of vector x. Okay, and I've given you some initial point, which is also a vector x naught. And so x1 naught is 1 and x2 naught, I'm sorry, x1 naught is, no, x naught, yes, x1 naught is 1 and x2 naught is 0.5. Okay, what I want you to do is I want to find the approximate value, evaluate this function linearly and quadratically, find the linear or quadratic approximation of this function at this given point. Okay, so what you do is for the linear approximation, So linear approximation means you should not have anything to the power 2. So it should be only the first two terms in your Taylor series. So if I write that, so this is a scalar, so x is scalar. If I write it in terms of vector, so it would be x. So L is the same as F, okay, don't get confused. I'm writing L just to denote that this is the linear approximation. And so it would be f of x naught bar plus the gradient of this. Instead of derivative, since this is a vector, you take the gradient times the difference or distance between these 2 points, okay? So when you work this out, you would get this to be the linear approximation of this function at the point x naught, okay? And if you do the quadratic, obviously you have to not only take 2 terms, but you have to take the third term as well, and you can neglect the rest, okay? So quadratic would be 2. So the more higher, so the higher order is the more number of terms you have, okay, in your approximation, the more accurate or the more accurate you would be to the actual function, okay? Functional value at that given point. So the lesser number of terms means it's easier to calculate because you have lesser number of derivatives to compute, but it would be lesser accurate as compared to the higher number of terms, okay? Is it clear? Okay, so now the necessary, if you go back to what we had studied earlier, we had talked about the necessary condition for x naught. So to be a local minimum, it was that first condition was the first derivative should be equal to 0. Second condition would be the second derivative should be greater or equal to 0. Remember, this is a necessary condition, not sufficient condition. That's why we have greater or equal to 0. We can prove this again by using Taylor's expansion, okay? So I told you that like there's a proof for Taylor's expansion, and this is the proof. So suppose you want to use this Taylor's expansion in some neighborhood of x naught. So let's say that within some distance of h or delta, as we have mentioned earlier, of x star, we want to evaluate this function and see what the value would be. And of course, h should be some very small value in order to ensure the continuity of the function, the sign of the function. So if you take this, if using Taylor's expansion, we again have f of this is equal to f of this star plus h times the first derivative plus some higher order. So O of h square. Any of you taking the course on data structures with me?
Yes.
Oh, okay. So for those of you who do not know what big O means that there is some term where the highest, for example, if we go back here, so there is some term where the highest order is 2. Right? Why not 2? That means the highest order of the value that we're looking at is 2. Okay, so that means everything else cannot be more than this value. Okay, so this would be the dominating term. So we do not actually. So this basically is saying that this has some number of terms, and the highest order of among those, the dominating term in those set of remaining terms would be h to the power 2. So we can actually ignore this because this is nothing as compared. This has no impact on actually the accuracy of this guy, okay, just to simplify our calculation. So we can ignore this. So if we ignore this, what we can do is we can say that now if I take this f star to the left-hand side of the equation, that means I bring this guy over here. So it would give me this guy. Sorry. So it would give me this guy. Okay, so I would get f of x star plus h minus f of x star. So this is almost approximately equal to this guy, which remains on the right-hand side, right? And also we do the same for if, so what we are doing is we are finding, we are expanding Taylor series to h on both sides of x star. So x star minus h would again be f of x minus of h star. So if I take this guy to the left-hand side, I would get this, which would keep this on the right-hand side. Now, what I have to check is for these two conditions, so that means I should find some, and we know that h is not equal to 0, it should be some value, right? So these two inequalities are satisfied, okay? So this is only satisfied when f prime x star is equal to 0, okay? Is it true? So these two can be satisfied only if this guy is equal to 0. Otherwise, there's no way that these two would be the same. Am I right? For some positive, so some non-zero h value. So the only condition which these two hold is when f prime x star is equal to 0, and that is actually when it satisfies the first condition. So we say that for what we say, the guy, the x star to be some minimum value, before and after the difference of the function values at some point h before and after x star, okay, should be greater than 0, and for that to be greater than 0, the derivative should be equal to 0 at that point, x star. Okay. The condition 2, which was this condition, it has to be greater than or equal to 0. Okay. So for that to happen, how do we do? Now what we do, we again use Taylor series, but since now we are taking the second derivative, so basically we have to take the term which has the second derivative in it. Okay, so the term which has the second derivative will be f double prime x star, and again we have other terms that follow, but we do not consider them. That's why you write them in terms of OH cube. So yes, OH to the power 3. So we can neglect this because this is an approximation. We are using approximation. We are not saying is equal. Okay. And at the minimum point, we know that f of x star is equal to 0. So what we can do is we can put this guy is equal to 0. So this will simplify to and bring this f of x star again to the left hand side. So I would get f of x star plus h minus f of x star, which is approximately equal to this remaining term, right? Now we have h squared. So previously I said h should not be 0. Now I'm saying that, okay, if h is not 0, it can be either negative or positive. But I'm saying over here, since it's square, so h squared will always be a positive, okay? So since this is always positive, therefore this guy needs to always be greater than or equal to 0 for this to hold, right? And therefore, when we have this condition, we can say, okay, at this point, we can now say that x star, okay, so basically, what I want to say is that when we have this condition, the point x star, this condition is used to start. So that means any point that is a point of inflection or saddle point will also satisfy this condition too. Okay, is it clear? Okay, convex function. We talked about convex function earlier. I have just brought it here because afterwards I made those slides. So basically, we know what this is. So we know what the definition of concave and convex is. So this is the main equation. We talked about this. I will not repeat or waste time. Look at the lecture video, and you can see it over there. Now let's get back to Fibonacci. We won't leave Fibonacci so easy. Okay. So what I want to show is I want to prove that the length of the final interval. Okay, over here I'm denoting it by IN because I'm using a different reference to reference books for proving this. That's why instead of LN we are using IN, but it's basically the same. Okay, so and over here instead of L0 we are using it as I1. Okay, so just to write in terms of intervals. So the first interval is actually the initial interval given to us. That means the difference of x of f minus x of s. Okay, and then what I'm trying to say is that now in terms of intervals, okay, the ratio of the size of the final interval would be equal to 1/f nth of the size of the length of the initial interval. And the proof is very simple. Does anyone know how to prove it? Has anyone looked into the proof? No, I guess. Okay, let's finish up with this proof, and then I guess we can do the polynomial based on Thursday. We have to finish this. Okay, so basically we know that in the first iteration, we always have 2 points to evaluate. So we, for example, if this is the initial interval given to me, let me bring my pen from 1 to 4. I have to find 2 points, 2 and 3, okay, which are the points at which I evaluate my function. So the initial length of the interval is I1. So assume that we I don't know, discard this guy, okay? So the next length, the next interval will be I2. So basically what I can write is this is very, very interesting. And then assume that again, when we discard this guy, the next interval would be I3 or this guy, doesn't matter. So the interesting thing is that I1 is always equal to I2 plus I3. Okay, so this is also the same as I3. Okay, depending on which part satisfies the unimodality test. So this is the same thing. So this is very important to start with. So I1 is also always equal to I2 plus I3 in a Fibonacci search method. Okay, and you can keep doing this, and you can say this for all the iterations that follow. So I2 becomes I3 plus I4, blah, blah, blah. The very last stage where the distance, that means this distance between these 2 points becomes so extremely small, let's say call it delta, that we can actually say that they're almost the same. So I can say that in minus 1 is equal to 2 times in minus this deltas, okay? And so this delta is very small, so I can say eventually it is equal to 2 times, or approximately, this is approximately the same as 2 times in, okay? And so what you do is you now write it down in the opposite manner. That means you write it down now from bottom to top. So in minus 1, you keep doing that until you find the general form, which is that for any j experiment, the length at in minus j would be f of j plus 1 times in. So this is 2. So you see, this is 2. This is 3 for n minus 2. For n minus 3, this is 5. So for any j, this would be what? J plus 1. Okay. So if j is equal to 3 over here, this was the Fibonacci of 4. So f of 4 should be equal to 5. Let's check. 1, 1, 2, 3, 5. Am I right? F of j, Fibonacci of 3 plus 4. 0, 1, 2, 3, 4. Yes. So f of 4 is equal to 5. Harasha? Is everyone following? Why is everyone sleeping?
No.
Okay, listen, guys. Otherwise, I will fall asleep. Okay, so if you do this for j is equal to n minus 1, so in the final, if you replace it for j is equal to n minus 1, and so if I instead of j I put n minus 1, this would give me I1 is equal to f of n in, and this is how you actually prove this equation. Okay, so this is interesting. Keep in mind. There's another approach to, okay, for those of you who have taken this course on data, or are taking this course on data structure with me, we studied about divide and conquer, and we studied about how to find the ith Fibonacci number in a Fibonacci series. And that was, if you remember carefully, it was, sorry, phi to the power I minus phi, the conjugate of phi to the power I, divided by square root of 5. And I said this is exponentially, the time complexity is exponential. So this is not something good because it's I to the power, phi to the power I. So that equation actually comes from here. Okay, so this is known as Binet's formula for finding the ith Fibonacci number. Okay, so we know the golden ratio. Okay, we just plug it in here and we can find the ith Fibonacci number without having to calculate the previous two. That means if I want to find f of n, I do not have to calculate all the previous all the previous n minus 1 Fibonacci terms. Okay, I can just directly put n over here and calculate. But again, for very large n, this takes a long time, and that's why it's not recommended. But there is an equation to do that. And the ratio of two numbers is this. I don't know why I've given you this. No idea, but it's good to know. So I guess this is what Sultan was telling, the ratio of two numbers is some constant, but this constant actually keeps changing, as you see over here. This is the equation for that. Sultan, are you here? Can you listen?
Yes, I'm here. I actually checked it after n. If n is greater than 5, then it is almost constant. Can I show you? It's very quick.
Show me real quick.
Real quick, okay.
Because this equation over here tells me something else. It tells me that it changes with the value of I. So it depends on what n value. So for what n value you're taking the ratio, it will change. Probably in the decimal part, but if you're looking at the only first few, what we say, positions, then maybe not.
Can you allow me to demonstrate my my screen, please?
Oh, okay. Okay, guys, wait, let me go here. new share, no, not new share, stop share and multiple. Yes, sir.
So here we go. Can you see my screen?
I can screen your C.
Okay. Let's define our Fibonacci numbers. 1, 1, 2, 3, 5, etc., etc. Let's say we have 20. Let's find the first 25. So these are our Fibonacci numbers. Everything is correct. And now we find the ratio of this Fibonacci number to this, and this, as we use in
No,
the
no, no.
Fibonacci
You're
method.
taking the ratio of two consecutive Fibonacci numbers.
Okay, that's also fine. Let's, but I haven't read it. But let's see. So let's say Fibonacci I. This is our last Fibonacci number, and we divide it with the one which precedes it. Everything's correct, right? I believe it is correct. So it is almost constant.
You see that it is, it's not constant. If you see carefully, it's converging towards the golden.
Yes, it is golden ratio. It gives us.
It's still not golden ratio. It's going towards the golden ratio. If you take n to be very, very large, it will, in terms of the accuracy, the digits in the decimal part, it will be very close to the golden ratio.
Yes.
Okay. Good. Well, where are we? Well, we have finished this. So on Thursday, we'll quickly go through the polynomial-based methods, and then we will start our next lecture on in the next week. And for this week, I'll put up some tutorials, and you'll be having a quiz on Tuesday. So please be prepared. Same as before, at 12 o'clock, you will find the quiz on Moodle. Download it, work it out, scan it, and upload it, okay? And this time your quiz will be something that you guys to study. So study well, and because I don't feel that you guys are interacting very much with me, and you make me sleep in class. So I want you guys to study well, and I will see how you do it in your quiz, okay? So the quiz will be whatever we cover till the end, till Thursday, including Thursday, this Thursday, okay? Any questions?
No.
Okay, take care of yourselves and see you on Thursday, guys.